So let's start. Just a small introduction and a little bit motivation for the project I'm presenting right now. My name is Dmitrii Stepanov. I am working at Yandex. Yandex is one of the major IT company in Russia, which is running lots of services. And 1 year ago, we launched a public Yandex platform, and I'm working there as a part of a hypervisor team. And because of this public prefix, one of our main goal is security. And in the context of hypervisor, it's the host security from virtual machines, from some kind of incorrect user's activity which can lead to memory leak, maybe DOS attack, maybe even VM escape. And a good way to improve security is fuzzing the interfaces which are available for the user. And for virtual machines, such interfaces are emulated devices. And today I will speak about virtual device fuzzing. First of all, I will tell what fuzzing is and what we are going to fuzz. Then I will tell how we implement virtual device fuzzing and what issues did we find during it. Then I will tell a little bit about our future plans. So, what is fuzzing? In general, fuzzing is the process of black box testing where the fuzzer generates some input and sends it to a test application and monitors its state. If it hangs, crashes, maybe handle the input without any error, all of this is pretty important. And what else is important? How the input is generated on each iteration. It can be randomized on each iteration, or it can be mutated, like using some algorithms like bit-byte flip or byte add remove. So the good idea is just to combine several approaches and use them all just to increase the source coverage, which is tested by fuzzing process. Nowadays, the fuzzers which are the most popular fuzzers are the guided coverage fuzzers. These fuzzers not only monitors the state of application, but also monitors the code paths which are used to handle the input. And this additional information really helps to prepare the data for the next iteration and again increase the source coverage which is tested. And in our case, we also use such fuzzer. It's AFL. I will tell more about it later. And what we are going to fuzz. So in cloud infrastructure, there is a host, and there are different virtual machines running on this host. There are emulated devices, and there is a transport channel between virtual part in guest and emulated part on the host. And in case of virtual devices, such transport channel is virtual queue. It is fully available for the user, and so it becomes the attack surface. And the error on the host side in the virtual request handler can lead to very bad consequences. As I said before, it can be even VM escape. So we want to secure this. Let's see from the high level of view how we are going to implement fuzzing. Well, we need a fuzzer engine which will generate input and send it to the test application using virtual queues. In our real case, the fuzzer engine is AFL, which makes the fork and run the test application just to monitor its state and code paths. And also AFL generates input, but we doesn't want to send it directly to the test application. Instead of this, we are using Unix socket to redirect it to the proxy application, and proxy application simulates the user activity, the user workload, by resending this input to the test application. And test application reports back the status to AFL. For the test application, we use both virtio-blk device implementation for SPDK and QEMU. But on the next slides, I will talk mostly about QEMU, just because it was more complicated to implement QEMU fuzzing because of virtual machine initialization, device initialization. But in fact, for SPDK, we used absolutely the same approach for fuzzing. So again, just to summarize what we implemented the full data cycle for the fuzzing, from IFL to proxy, from proxy to test application, and from test application back to AFL. Let's see in more details on each communication step. The first step is IFL proxy communication. The problem here is that by default, AFL is using std-in and some kind of test shared file as input, and if we use such approach, then we need either enhance AFL itself to support virtio-q communication, but it will complicate the fuzzer logic, or either we need to enhance QEMU itself just to support std-in as input. But it will make the difference between production case and the test case. We also don't want it. So we had another idea. We used proxy, which IFL sends data to the proxy application, and proxy application knows what will be the backend for the fuzzing. It can be SPDK, it can be QEMU. In fact, it can be even some kind of TCP/IP server. So the good idea here is that IFL fuzzer is independent from the transport backend channel. When data is received by proxy application, it resends it to the test application. For QEMU, we used the QTest framework to initialize devices, to read, write memory from virtio-qs. So it's really good. And when data is received by the test application, we need to do two things. First of all, is we need to monitor the code paths, which is used for handling, and the second one, report back the status. As for the code paths, we used AFL CLang compiler to instrument the source code, but we really didn't want to instrument all the QEMU source code because it will complicate the fuzzing. So we instrument only part of QEMU. It's virtio-blk device implementation, and also virtue descriptor handling. Then we need to report the status back to AFL from test application. The easy way to do it is just to call exit on each error and success path. Well, it will work, but will work really, really slow, because on each iteration we will require to reinitialize full virtual machine, reinitialize device, and it will just slow down the whole process. So instead of this, we used IFL persistent mode. In this mode, we used 6-stop signal to report the status back to AFL. And in this case, AFL can use the same test instance for the next iteration, and it's very fast. The only drawback here is that on each iteration, device changes its state, and we should be ready to reset its state back to the default state. That's what we implemented also in QEMU for fuzzing. So, just to summarize what we implemented, again, it's a full data cycle from IFL to proxy, from proxy to test application, and from test application back to AFL. What is also important for fuzzing is what data we used for fuzzing. We tried different approaches. One of the approach is just to use part of guest memory, which is available for virtio-blk device, and just randomize and fuzz the virtio-blk device using it. This approach worked, but was pretty slow because, again, on each iteration, we need to reinitialize the whole guest memory region. Even it's only the part, it can be like several hundred megabytes. So it's not good. We used another approach. We used existing API to craft a virtue descriptor table and randomize only virtio-blk requests. Well, this is a pretty fast approach, but the only problem here is that by using existing API to craft virtue descriptor tables, we really did not hit the error paths. So the source coverage, which is tested, really not so good. So we used the third approach. We randomized not only virtio-blk requests, but also virtio descriptor table itself. And from the viewpoint of source coverage, from the viewpoint of speed, it shows just the best results. So we use it for fuzzing. What is also important for fuzzing is crash management. And by saying it, I mean we need something to catch the crashes, catch hangs, restart after crashes, catch inputs which lead to the crashes, maybe report some statistics. And all of these is in fact implemented by AFL, so it's great, just use it. What I want to say that some of the issues we found it like in several hours. Some of the issues were found in several days or even weeks. So to get the most from fuzzing, it should be like the endless process which is integrated in your CI, because you never know when and where new issue will be found. So let's see what issues did we find. First of all, we hit several assert errors in QEMU. One of such errors is shown right now on the slide. If the size of indirect virtio descriptor table is set to null, then it will hit the error and virtual machine will crash. It's not really a critical issue, because by doing this, the user can crash only its own virtual machine. But anyway. Next issue we found was memory access violation in SPDK. If the memory region, which is available for virtio-blk device, is not aligned to huge page size, then there will be a small possibility to read or even write to the memory of other virtio-blk device. Well, it sounds really bad, but in fact, it was not so critical, because this not aligned case is very rare custom case and documented like unsupported in official documentation. But still, it's pretty interesting what can be found by fuzzing process. Another issue in SPDK which was found by fuzzing process was the endless loop. And in fact, it was a vulnerability. The user can craft such a virtio descriptor table where the first entry points to the second one, the second entry points back to the first one, and it will be like the endless loop. And in this case, the handler on the host will run this loop like forever. And if there are several virtio-blk devices attached to this handler on the host, then all of them will hang. So it will be like DOS attack on block host subsystem. So in fact, it's a good point to update SPDK on your host if you are using it. The scheme, fuzzing scheme I've just described is running right now on our host, so we're trying to find new issues, but we want to improve it. First of all, we want to improve the number of the devices we are fuzzing. For now, it's only virtio-blk device, but we also want to fuzz virtio-net device, virtio-soc device, and so on. Then we want to increase the surface, which is used for fuzzing. So for now, it's only virtio-queues, but we also want to add PCI, at least PCI. We want to increase the quality of the start input. So just to increase the source coverage, which is tested by fuzzing. For the QTest framework, the nice enhancement will be direct memory access, so to increase the fuzzing process. So we will not use QMP commands to read-write memory. And the test case verification will be also a nice feature to have. All the changes for QEMU, for AFL, are published right now in our GitHub Yandex repository. You can use it, you can check out it, review, maybe have some fun. So fuzz the code for fun and profit. Thank you very much for listening. Hope you enjoyed the talk. Any questions?
Hi.
Hi.
Great work, thanks. I didn't quite understand if you restart parts of the emulator between every test, or if you just leave it running. Do you just run one test and then you restart it and go again every time?
You mean why we need to reset the device state?
How are you doing it?
So we have the virtual queues, which have different fields in virtual ring, like available and so on, IDs. So we needed to reset back to its default state. We just write in memory in the guest memory.
Right, and on the emulator side, are you restarting anything between each test of AFL?
No. It's just the same test instance.
Okay. Yeah, we did something very similar for our vhost SCSI backend. And what we did is we stubbed out everything around the queue handling code. And we brought a very quick thing to start with a fake, very small guest memory just to fuzz that in.
Mm-hmm.
And we found it valuable to restart the emulator every time, because a lot of the invalid input that you throw would then, a lot of the time, just stop the device from picking up new requests.
Yeah, that's what code you need to debug, in fact, while implementing.
Yeah, I was wondering if there were plans to do something more, like if you have the backend restarting between each test.
I noticed the slide you have of the AFL screenshot, that the stability is really low, like 25%. Can you expand on that?
This is
27%.
Yeah, in fact, it is just some kind of run. It's mostly about AFL usage, about AFL statistics, and in fact, no, can't say the correct meaning of. I think
no, it means that when you rerun samples that already had a result, you only get the same result 27% of the time, which means your fuzzer is not deterministic. So usually you want to get that up. So I'm just wondering if you know which parts are non-deterministic.
No.
Oh, okay.
Are you reacting or new question? New question. Then he was first.
Hi.
Hi.
It seems that several organizations are all doing fuzzing, and everyone is doing it downstream. So it would be great to fuzz upstream too. Do you have any plans to upstream your work?
Yeah, we. First of all, I believe we want to fuzz the changes in AFL, because in fact AFL was not published in official repository, I think, till July this summer. So I believe we will start with this. And for QEMU part, I want to implement the VirtuaNet fuzzing also, just to see how this proxy scheme I've just described work. So it's not only for one device, so it's for two devices, and it will be like understandable how to add new devices for fuzzing. After it, I think it will be a nice idea to upstream, or at least to talk with the community about these changes.
Thanks for your talk.
Yeah.
First question, which sanitizers do you enable for QEMU?
Well, in fact, we use some hardening, stack hardening, so not really very much, because AFL itself has some issues with using ASAN on x64 platform. Like it requires lots of memory, like 20 terabytes. It's not like it requires right now, but during fuzzing, byte by byte, it commits this memory and you're out of memory. So for now, we do not use ASAN, but we are going to use it.
Didn't understand. You mean that you enable ASAN for AFL?
No.
It is really easy to build QEMU with sanitizers and it works fine.
Yes, but if you are running it using ASAN, if you build such binary, QEMU binary, which is was built using sanitizers, when you are running it under AFL, you will need lots of memory for 64 platform, not 32. For 32, it's okay. But for 64, you will have this big memory issue, and you should think how you will resolve it. Okay. Of course, if you're fuzzing like for 1 hour, maybe one night, it will be okay. But if you like fuzzing for several days or even weeks, it will be a problem.
Okay, thanks. I didn't know that. And second question, how your process of fuzzing so how do you reproduce the bugs which you found?
So in fact, all these slides shows the input which we used. It's just binary files like 64 bytes, which we used as start input. If AFL catch some crashes, it stores the crash and it's the similar file. And we use this file to put it like input to the proxy application, and proxy application redirects it to QEMU again, or SPDK. And in fact, in this case, we use the production case of QEMU and SPDK without any changes, just to be sure that it's a real crash.
So when QEMU reports about the fault, it points you to the
we have
dump file.
We have such a virtue descriptor table, which we will send it to QEMU.
Okay, thank you.
Yeah.
Hi. So I had a very similar question to what Stefan asked. So did you get a chance to? Did you happen to take a look at if your work, how difficult it is to integrate your work with libfuzzer? Because from the documentation, it looks like there is a way to make AFL work with libfuzzer, because that way we can probably submit these tests to OSS fuzz.
Yeah, I took a look into it, and in fact, my personal opinion, it will be nice to have both AFL fuzzing and libfuzzer fuzzing. It's not like they are going to integrate into each other, just from my point of view. The good point here is that, as I see it, libfuzzer is like unit testing fuzzer which runs unit testing. And AFL, at least in our case, is more like fuzzing the whole production case of QEMU. So you will run the full stack. So yeah, that's the point. I want to see both implementation and run them both simultaneously. Yeah.
We use fuzzing, but we only do it on one machine, and it takes weeks to find anything. I mean, how many machines do you do the fuzzing across? How many cores, that kind of thing?
For now, it's just one machine, which is running into several processes, and that's all. So, in fact, the start input is very important to fuzz, to find something. So it's like very small details which can show the issue or not show. So yeah, maybe this is a problem.
Okay, thank you.
Thank you very much.